I bet you can see. So, as I said before, welcome to this training on digital manufacturing, which is part of the European project SMERF. So, what is this? SMERF project? So the SMERF project is Interreg Central Europe project, which started almost 3 years ago now, and involves 8 partners from 7 countries of Central Europe, and has the purpose of supporting low and medium tech SMEs in the transition towards the future. And there comes the name with the acronym SMERF, Small and Medium Enterprises Ready for the Future. So the idea of this project is to help not only the SMEs in facing the challenges for the futures and getting ready for the new trends and markets and so on, but also to provide the higher education institutions and the intermediaries, which are these entities expert in supporting SMEs, to help the SMEs in facing challenges. So generate a bridge between the research and supporting entities and SMEs, collect expertise, and give a look at the challenges and there's, of course, possibilities of the future for the SMEs. So actually this MERF project is based mainly on 4 pillars. So the consortium identified in the proposal 4 pillars on which SMEs should focus on, should be analyzed, should be evaluated, and should try to follow the trends. So we have as a first pillar number 1 has been defined as the innovation culture. The innovation culture is the pillar which is more related to the people who compose the company. So it's not strictly technological, it's not strictly related to resources or everything, but it's more about how the people think. So for an SME, it's really important to keep the idea of being friendly to innovation, because especially in SMEs where there are few people rather than big companies, it's really important that everybody is involved in the innovation. So the innovation must be something in the mindset of the people of the company. And therefore, naturally, it's important to invest in research and development, and also that the leadership of the companies, so not only the people who are working, but also the management, has a clear view on how it is important and what's the impact of having innovation culture. Then we move on the maybe more common digital manufacturing, which nowadays is everywhere. It covers mostly the production service, the production, but also the companies that provide services. And it underlines that it's clear that it's important nowadays to be advanced in this sector, to integrate digital solutions in production process, but also in supply chain and logistics and so on. And so it's important to be proactively adopting these new technologies to follow the trends, and especially maybe with the big companies, and to keep up to date. Then we have the open innovation 2.0 and sharing economy, which are two concepts. We have the concepts of open innovation, which means that the company is ready to share ideas about how to provide a service or produce a product, and also to know how to handle it. And also sharing economy, which means more sharing tools and resources. Rather than investing on buying, for instance, machines and so on. And this is another key factor, especially for SMEs, which maybe lack the budget for big expenses and big investments with a high return of investment time. Then we have the last pillar, which is maybe the most common nowadays, which are green and circular economy and sustainability. So also SMEs, which in the Central Europe country, actually, they cover most of the supply chain of also big companies. It's important that also SMEs have somehow sensibility toward what is the impact of footprint, the footprint in production, and to keep an eye on what they are doing and implementing optimization to minimize waste and to reduce pollution. So the countries which are involved in this project actually are, as we said before, 7, and we have 2 countries which are considered to be a leader and to be more up to date in these areas, which are Germany and Austria. And the idea was to work together with other countries such as Poland, such as Italy, Hungary, Croatia, or Slovakia, to try somehow to transfer the knowledge from these countries, Germany and Austria, which are leaders, to the other countries, and collaborating together to get also an overview on what's the situation for SMEs all over this area of Europe. So what we managed so far to reach, we managed to set online an inspiration knowledge base based on study on state of the art, on good practices. We had webinars, we made some interviews, and we offer some innovation service. Then we have our SMERF diagnosis tool, which is a powerful tool for self-assessment of company, which has been tested already on 160 SMEs successfully, and on which we formed as a consortium more than 80 promoters, people somehow connected to the partners, which had the job of spreading the knowledge of the usage of this tool. And then we had the Green Market, which was an event held in Austria, where the consortium managed to collect some SMEs to get to know what are the needs of big companies and to know each other, making some network, and also present their services and have an idea, have a close look at the reality of big companies. Now, right now, the consortium is involved in the final phase of the project, and we are actually bringing SMERF to companies a bit more. And we are now implementing the individual super program, where companies that we selected are being individually supported with mentoring, expert consultations, and offer of services. Then we are organizing study visits in which we will bring some SMEs to companies or high education institutions. And we are doing these kind of trainings. We are going to do a total of 8 trainings. Most of them are already done. We have covered all the 4 pillars, and you can get them on YouTube and have a look at them, and have a look at the 4 pillars, and where experts actually brought some knowledge to the SMEs with some study cases and best practices. So what we offer so far to an SME, as I said, we offer these trainings, which are online, and so pretty soon they're going to be completed, and they're going to be all available on YouTube, where you can get technical knowledge, and as I said, best study cases and so on. And we offer the SMERF diagnosis tool, which is already in a let's say in a beta version. It's working fine. It's giving results, and will be updated at the end of the project. And it can give for what concerns this tool. I've personally got the feedback, and other people from the consortium, other partners, that it can give you quite a good insight of your companies. Maybe it can give you some ideas of what you need and what you don't need actually. And moreover, it generates an assessment of your company and give you some suggestions on what characteristics you should focus on as an SME to keep up to date. So last but not least, all these services that I've talked about, so the SMERF diagnosis tool and the trainings, are not are free of charge. So you are free to sign in the SMERF page and to try out the test, or to have a look at our trainings, and everything else is in the innovation knowledge base. And for any questions, if you would like to know more or something, or if you would like to visit the pages related to the SMERF Interreg project, then you can simply reach us at our social, or you can also write directly to me if you need any information, especially for the Italian area. Me, myself, I'm a PhD student from the University of Genova in Liguria, so this is my region. And then I'm done. I would like to introduce Alessio Caporali, which will take the floor and present his training about digital manufacturing. Alessio, the floor is yours.
Thanks, Federico. Okay, good. So
I can see.
Yeah, great. Maybe we'll put this here. Okay, so morning everybody. So and thanks for joining this talk. So today I'm gonna talk a little bit about deformable objects in industry, and in particular how we can move the robots to do manipulation tasks with these kind of objects. And I'm gonna focus predominantly over objects like cables and wires. And you're gonna see what we did both at the beginning at the university and what we're doing right now, pushing forward in a spin-off project of the University of Bologna that is called ROBOSECT. So first, I would like to introduce myself and a little bit on who I am and what I do. So I am currently an assistant professor at the University of Bologna. I obtained my PhD last year with a thesis titled Robotic Perception and Manipulation of the Deformable Linear Objects. So as you can see, this is kind of the main topic also. It has been the main topic also my PhD. And I've been conducting indeed research on deformable objects since 2020. And I hold a bachelor and master's degree in automation engineering from the same university. At the same time, I'm also involved in a spin-off project of the University of Bologna. It's called ROBOSECT. And that's kind of my main affiliation for today that I'm gonna use. And this spin-off was established last year. And ROBOSECT is a technology-driven company that is focused on robotic solutions for industrial applications, and specifically robotic solutions involving electrical cables and wires. So this is the outline of today's training. So first, I'm going to introduce in a general term what are deformable linear objects, so that everybody kind of understand when I'm talking about these kind of objects. And then I'm using three main example of challenges in terms of deformables in manufacturing. So we're going to use this. I'm going to present these three main challenges. I'm going to use them as a ground floor for what we need right now in terms of robotics. And starting from these three main challenges, I'm going to move to present what we did during the Remodel project that was a European initiative that ended 2 years ago. And this will allow me also to characterize how we move from the university with this Remodel project to establish ROBOSECT as a company, as a spin-off project. And this is going to conclude a big introduction that I will give you today. And from that point forward, I'm going to do more two main aspects. I'm going to talk a little bit about the perception task of these deformable linear objects. And then I'm going to talk about the second main topic of today, that is the manipulation part. And at the end, I'm going to draw some conclusions, some remarks, and some takeaways about my talk. So let's start with the introduction. So if we think nowadays in terms of robotics, we have that robots are really effective in repetitive, well-structured industrial tasks. So like if we think about welding, painting, or also assembly of mass-produced components. However, the robots still face significant limitation when it comes to autonomy and adaptability. And many industrial processes are indeed involved in dynamic environments, so tasks that can vary from one cycle to the next, and also products arriving in unpredictable conditions. So these challenges are also even more pronounced if we think about having the deformable parts inside the industrial process. And the deformable objects are, for instance, wires, cables, or wiring harnesses are example of these deformable parts that can be present in the industrial process. So they are flexible, complex objects where they are very sensitive to the manipulation part. So this makes them extremely difficult to be handled with like a robotic system, with the conventional, let's say, robotic system that we have right now in industries. And that's why if we want to enable robots to work with these kind of objects, we need to improve in terms of perception, manipulation capabilities. And this is indeed an area of research that is gaining a lot of attention, like in the last 5 years. It's gaining a lot of attention. A lot of works have been done in these topics. And in order to, I think, better understand the DLOs, so these DLOs is the short way in which these objects are usually addressed in the research community. I just wanted to introduce the three key objects. So the first one, a classical example of DLO, is a wire that is a single unipolar conduction element that we cannot separate into different objects during manufacturing. So it's like the basic component. And the second one is a cable that is like a bundle of wires that is grouped together into like a protective sheet. And indeed, a cable can be separated into individual wires, for instance, to be connected to a terminal or to other things. And finally, we have also a big player in this kind of objects in industry is the one about wire harnesses. So a wire harness is composed from multiple wires and cables that are grouped together to form a complex network with multiple branches. And this wire harness is serving as like the electrical backbone for many automotive, aerospace, and also electronic applications. So these are three classical examples of DLOs, and they are the object that I'm addressing today as deformable linear objects. So in terms of challenges, so in modern industry, wiring tasks remain one of the most complex and labor-intensive processes. And so I'm going to show today three representative examples, and this will allow us to understand how the task is currently performed, and most importantly, why robotic solutions are still missing. And these three are the examples that I'm going to show today. So the first one is switchgear wiring. So this is the process of assembly like electromechanical components over some rails inside like an electrical panel. So we need to lay down the cable in between the pairs of component, and we need at the end also check the connections to verify that the assembly process was performed properly or not. The second one is wiring harness manufacturing, and this is the process of in which we assemble a bundle of wires over like a specific board, or usually a simpler like pin board, like the one shown in the slide. And this is in order to obtain like the final wire harness. So this is like the construction of the wiring harness part. And the third one is about cockpit harness assembly. That instead is the process of like installing large wiring harnesses with many branches over like a specific structure. In this case, we are addressing the car cockpit. So we have the wiring harness of our car, and we need to assemble that during production on the cockpit. And across all the three challenges, the common bottlenecks that we're going to find, like when we're going to analyze in a moment, all of them are complexity, high manual effort, and low level of automation. So I would like to start with the switchgear wiring. So as already introduced, switchgears are critical elements in many fields like power generation, industrial machines. Also, we have in our homes, we have electrical panels. And so they are critical elements, and that's why also the wiring inside them must be like assembled precisely and be safe and durable. In terms of manufacturing, switchgear wiring is one of the most demanding assembly tasks, and the process itself is challenging for several reasons. It challenges because it requires human-like sensitivity. So in order to deal with unpredictable occlusions and also the variety of possible layouts of the component inside, it also involves clearly the manipulation of wires that are deformable and are hard to predict, and they do not behave like rigid components at all. It also relies heavily on like paper-based documentation. So the worker must read, interpret, and translate this documentation into like a step-by-step assembly sequences. And so this requires both time and experience, and this can also represent a huge source of errors. There are also no standardized production lines. So usually these products are have layouts that vary a lot between one product and the other. So many products are highly customized, and most of the time they are unique. So mass production is especially difficult to be integrated in this kind of products. So because of all of this, most switchgear wiring today is still done manually. And typically the process begins with a crimping machine. So there is like a machine that prepares the wires by cutting them to the right length, ensuring that they are of the proper size and color. It's gonna like print or label them with a machine, and then these wires are grouped together according to the wiring plan. So after this wire preparation step, that in which we can have some kind of degree of automation, there are some machines that can do that. There is like a repetitive task performed by a human operator that's going to be like the one of reading the switchgear schematic and identifying like the next connection from the documentation. Then the operator is going to locate the component to be connected inside the switchgear, and it's going to select the correct labeled wire, because obviously you need to put the correct wire between the components based on the documentation. And then it's going to connect one end of the wire to the designated component. It's going to route the wire carefully along the correct path. So placing it inside, usually there are wire collectors that we can see also on the slide. And then it's going to connect the other end of the wire according to the schematic to the other components. So this is just for one wire, and this process, so once completed, it needs to be repeated for every wire that needs to be assembled. And so usually the process of assembly of switchgear wiring can take up to several hours. And it's clear that this process is highly repetitive, time-consuming, and labor-intensive at the moment. It also highlights this process, the bottlenecks that we are now in the process. So we rely on human dexterity, the difficulty of handling deformable wires, and the variability of product design. Okay. And so this is one example in which robotic solutions are currently really like the degree of automation is really low, and in which robotic solutions can be a step change in the process. Good. So the second example that I want to bring today is the one of wire harness manufacturing. So this is similar to switchgear wiring. It's also the manufacturing wire harnesses is also another time-consuming and labor-intensive process that is affecting today's automotive and aerospace industries. In the automotive world, let's say a wiring harness can be considered like the backbone, the nervous system of our vehicle, and it's going to be used to connect all the power components like the speed sensor, climate control, lighting, safety devices, infotainment, and so on. So in this case, the process begins with the wires being like cut to precise length, sometimes printed with labels also in this case, and stripped at the end in order to allow the connectors to be inserted. Indeed, the connectors inserted are bundled and arranged in a pin board following a specific layout. So this, for example, is a part of the pin board. And these wires are then this step are repeated over and over until the complete wire harness is constructed, is assembled. And usually also then there is a phase in which the wires are like covered with some protective sleeves, and they're either like installed then at the end directly into the vehicle if the assembly is done, the manufacturing wire harness is done internally, or it's like shipped for later integration. So this for the automotive, and very similar the case is also the case for aerospace. The main difference is that in the aerospace case, the harnesses are usually made of multiple groups of pre-connected cables. So at the end, the wire harness itself is even larger and more complex, because obviously also if you think about the aerospace sector, the size of the planes and everything is way bigger. So there are a lot more cables. And also both from the automotive and aerospace industries, the main goal of this during this manufacturing of harness should be the one about safety, because this device need to sustain like functional tests at the end in order to verify that they are safe to use. Okay. The third example is the one of wiring harness assemblies. This is a bit different from the previous ones, because this one instead we have the case in which we already have the wiring harness. So the wiring harness like the one shown here. So this is like the wiring harness of a car cockpit. And so we already have the wiring harness, but we need to bring to assemble that on our car cockpit. So right now how it's done, we have that at the beginning of the car cockpit assembly line, the harness is going to arrive in a box in an unpredictable configuration, like here, and then the worker must lift this wire harness. Is going to spread it across this metal plate that serves as like the foundation for all the cockpit components. So several wire harness branches, or several branches of this wire harness that needs to be threaded through some narrow openings, so like pulled from the other side of the car cockpit, and then it's gonna be they're gonna be secured into place in some ways. As you can see, this process requires high dexterity, significant physical effort, and constant attention by the worker. And so the result is a process that is time-consuming, like the previous one. It's also very ergonomically demanding and prone to variability. It's very ergonomically demanding because these wire harnesses are very complex and very heavy, can weigh up to 20 kilos. And so for a human operator, it's quite a tough job. Once this wire harness is secured in place in the correct way, then usually electrical testing phase is performed. So the worker is going to connect the harness branches to some cockpit electronic control system, in order to perform automatic functional checks. And this connection of the connectors is done manually right now, and usually requires 2 arms, because the connectors are quite difficult then to be secured together. So also this is quite a task that should be make automatic with the robotic system, but is currently performed manually. And at the end of the assembly line, then the wire harness is the section of the wire harness that are not connected are covered with these organizer bags, And this before like transportation to the final assembly plant. So maybe there are some parts of the car copy that needs to be assembled later. So the section of the wire harness are organized in these packs, and these to prevent damage, tangling, or also misplacement of the wires. And so this can be like facilitate the integration later on. So from an industrial perspective, also this the last sample, but it's true also for the previous ones, we can see that we have a strong reliance on manual labor in these highly repetitive and also ergonomically difficult processes. We have a very low level automation, despite the complexity, the cost, because this has a cost quite important, and also the importance of wiring harness in general and wires in the automotive and industrial sectors. So these are the three examples that I wanted to discuss today with you. And these challenges were exactly like some of these challenges were directly addressed in the Remodel project. That was a European level initiative active between 2019 and 2023, and was funded under the Horizon Europe, Horizon 2020 Research and Innovation Program. So the goal of the model was to focus on this task. So the manipulation of formula objects in, for instance, wires, cables, harnesses, and also plastic tubes. We're seeing that these components are essential across many sectors like automotive, aerospace, electronics, and also medical. We are not talking here about the medical sector, but also we have plastic tubes and many other similar objects also in the medical sector. But the flexibility and the unpredictable nature of these objects makes them extremely difficult for traditional robotic system to be handled, to be manipulated, as we have already discussed. And so the project goal was to develop novel algorithms, methods, and approaches that will enable robots to manipulate these deformable objects with a reliability that should be comparable to the one of rigid objects. And so the goal was that by doing so, by reaching these new methods, new approaches, we can deliver like many benefits at the industrial level, like higher productivity, improved job quality, better product quality, and also reduced costs. So this was during the project Remodel. So we did a lot of work in this aspects. And indeed, the Remodel project was coordinated by the University of Bologna and within the robotic group, of which both I and like myself and also several other founding members of ROBOSECT were part and are currently part of. And so given the significant like many technology that we developed during Remodel, it was kind of like a natural step to explore how we could like bring these new methods, new approaches, new tools, we can transfer that to the market. And so that's why we decided at the end to establish ROBOSECT. And the mission of ROBOSECT is to, exactly this one, is to bring the robotic several technologies that we were pioneered in Remodel into real-world industrial applications. Specifically, with ROBOSECT, we decided to focus on the automation of the switchgear production. So the first challenge that I mentioned today. We have seen that currently these electrical panels, switchgear manufacturing, are still assembled largely by hand due to many problems like the high variability of components, the frequent customization, and the complexity of wiring. So this manual process introduced many like risks like human error, also longer delivery times, and also dependency or highly skilled worker, and also the need of quality control. So right now the quality control is kind of inconsistent due to the manual assembly process. So with the Remodel, we try to address this domain. And in particular, if we look specifically at the electrical control panel manufacturing in Italy, so I'm just focusing on Italy, we have that each year we around 15,000 panels are assembled manually. And so this translates to roughly 10 million cables being routed and like connected and manipulated by hand. So there is a human operator doing this 10 million cables assembly every year. And this is so an enormous amount of manual work. We have seen that the production process of this electrical panel, these switch gears can be divided into three main phases to simplify a bit what I already described before. So in the first phase, in phase one, we have the, the assembly of components on the racks. So each switch terminal device must be positioned precisely according to the design specification. So this is a task that demands accuracy and attention to detail. There is the operator inserting this component over the racks, over the rails of the panel. But there are some machines that are able to do this kind of task. So there is a bit of automation in the phase one right now. In the phase two, we have the cabling phase, which is right now the most labor intensive. So because we have at every wire, we need to cut, stripe, route, and connect the wire to the correct terminal. And this is the very repetitive, time-consuming, and ergonomically demanding task that we described before, in which we have this human operator looking at documentation and doing this job. And there is no automation enough for this phase two. And finally, we can also introduce a phase three that is about quality control testing. So every connection that is done right now by human operator must be verified to ensure that safety is satisfied, proper functionality is satisfied. And right now, also this functional testing, yes, this quality control is done largely manually, and therefore is itself prone to error. So we can have errors even in the quality control. And so it's clear that across all these three steps, three phases, we need automation. And so we need to have a machine that is able to assemble these components automatically. It's able to do the cabling between the components automatically, and it's able to control the result of the assembly process in an automatic way, in order to be repetitive, in order to be consistent, in order to have like no human error in the loop. So these regards, we already done some like proof of concept of the solutions proposed by ROBOSECT that are covering both phase two and phase three. So in the cabling phase, so I'm just looking right now at this phase two. We have that we have a system that is able to identify the components and is going to automatically route a wire according to the CAD design. We have a vision system with some learning AI-based solutions that is able to do that, and also some clever like trajectory planning for the robots. And in testing phase, instead you can see like a proof of concept at higher TRL that is in which the robot are performing. In which the robot are autonomously performing quality checks on the switchgear connection. So we have this dual arm station with this specialized end effectors that are going to check the quality of the connection between pairs of terminals based on the product design or the CAD design of the panel. And so that's why here in the slide we have at the top this illustration this shows our digital twin, let's say, of the control panel that is generated directly from CAD data. So in this proof of concept, we are combining very advanced perception capabilities for both like components and cables, and also manipulations capabilities, in order then to bring robotic solutions to this switchgear assembly task. Our long-term goal is to achieve full automation for both wiring and testing for these two phases, So in order to create like a fully integrated end-to-end workflow for electrical panel assembly. And a question that I can have is that switchgear manufacturing is indeed quite specialized in niche market. That's true. But we can say that the presence of electrical cables and like wires and this object that I'm talking about today spans many critical industries. So we've seen automotive wiring harnesses is another example, and also aerospace system is another example, but we can think about also large-scale data centers. And across all these sectors, we have the same challenge. So we have a high manual, repetitive, and labor-intensive process. So with that relying heavily on human intervention. And this not only increases production times and costs, but also introduce variability and potential errors in quality. And so with ROBOSECT, we are like now focusing just on the control cabinets manufacturing, let's say, niche, but our vision is to bring automation and robotics, let's say, to all these cable-intensive industries. And so we want to have like a future where robots can handle like complex cables and wiring tasks across multiple industries, reducing human strain and maintaining high standards of quality and repeatability. So this is our goal. So just to give a background and like a bit long introduction on what we are addressing in terms of what like past project research and also right now also in terms of spin-off project. And given that, I would like to start discussing more about the actual methods and the actual projects that we developed and that we are trying to use in this spin-off project, kind of like bring it to a higher TRL. So I just talked about like the current situation, but if we want to see robots that are able to handle like these cable-intensive tasks in industry, we need several technologies. And these technologies can be grouped into two main areas. So perception and manipulation, that's going to be also the way this seminar, this talk is going to be organized. So in terms of perception technologies, for sure, and here I'm trying just to summarize a bit the ideas. So for sure, we're going to need advanced 3D vision systems. So to be able to detect and localize cables, connectors, and also these panel components in 3 dimensions in an effective way. We're going to need the deformable object tracking. So to be able to continuously monitor the changing shape of wires and harnesses during the manipulation, so as they bend, twist, or stretch, and also possibly also be able to handle occlusions. And we're going to need an integration with the CAD digital twins in order to map perception data directly to design specification. In this kind of industries, usually we have like some design, some CAD data that we can use. So we need to have this kind of integration in order that our robot can like follow the intended layout precisely by doing this mapping in terms of perception to this CAD digital twin. Concerning the manipulation, we're going to need for sure some physics-based modeling of these deformable objects in order to predict how cables will behave during grasping, during routing, during insertion, and so on. We're going to need some adaptive control strategies to be able to adapt online to some changing condition and minimize the gap of this physics-based model to the real-world behavior, because there is going to be for sure a gap. So we need ways to be able to map this our real system to our model. And we're going to also have in terms of manipulation the need of some dual arm coordination, because these objects generally requires a dual arm type of manipulation. We're seeing this both like for switchgear wiring, but also for like connector insertion in the functional test. So we need usually these dual arm systems. And so we need this kind of technology to be developed. So the remainder of this talk is going to be dedicated to address some of these aspects. So I'm gonna take some of these and I'm gonna discuss more about some of these. And so we're gonna see what we can do, we have done, and what needs to be done concerning these technologies. Okay, so I will start talking about data generation. So I will start addressing the perception part, and in particular data generation. So why we need data at all? So, and how can we generate the data? So if you want to perceive these kind of objects, so like cables and wires, these objects are everywhere in industry, but because they like bend, twist, and come in many different shapes and colors, and also the way in which like they are made, like the very slender shape, so they are very hard for traditional like computer vision system to handle, to be detected. So all the techniques like, for instance, color thresholding, so like picking out a wire by its color, or like edge detection, so like finding lines in the image, or even background subtraction, that's removing everything that's not the object of interest from the image. All these kind of like standard techniques, often they fail when the lighting condition changes or when the background is cluttered. For instance, when we have like in this image, a metal backplate in the scene, that's gonna affect a lot the lighting of the image. So these standard techniques usually struggle a lot. Deep learning offers a more powerful solution. So perception system can be trained to recognize, to track wires and cables in an effective way. But there is the problem of learning solution, that we need a lot of high quality and image and label pairs, and collecting and marking these images by hand is so creating this dataset by hand is a slow, tiring, and also error-prone problem, which makes it hard to scale up automation in real factories. And there is also another complication, that's for flexible object, the standard like bounding box detection are not enough, because for to understand how a wire wire, for instance, is placed in the image, you cannot just draw a bounding box. You need to actually describe the shape in the image. So you need more than a bounding box, and we need actually a detailed segmentation. And this makes the creation of the dataset even more complex, because it's more difficult. You need to label each pixel precisely, and so on. So I'm talking about segmentation, and there are two types of segmentations. So the first that can be used for wires and cables, the first one is called semantic segmentations, in which we kind of label every pixel of the image with the type of object that we are looking at. So in this case, like black means background and white means wire. So this is kind of the result of a semantic segmentation mask that we can get for this image. And but I think it's clear from this image here that this is useful if you want our robot to understand where there are wires and where there are no wires. So for instance, if we want to avoid collisions with wires, we want to go on a region of the image without wires, but cannot be used to manipulate a specific wire, because we cannot distinguish the instances of the wires individually. And that's why there is also another segmentation type of segmentation that is called instance segmentation, in which instead we label every pixel with both the type of the object and a unique ID for each individual object. So in this case, there are three wires that are lined together in the image. As you can see, we can kind of like distinguish each of them. So this red one is going to describe one wire, the green one another one, this blue one the third wire. And so this is useful because it's going to allow our robot to pick, to route, or connect a specific wire. And so this is very, very useful for manipulation purposes. So this is the situation. So we need ways to generate a data set for this kind of task, for the semantic segmentation, for the instant segmentation task of processing input images with the learning system. And so we need a data set to do that. And in the next slide, I'm going to show different ways to generate data set for this kind of tasks. Both like some methods are based on a minimal effort by means of human operator, and instead some others are completely like human-free, it's completely automatic and without effort from a human during the like generation of the data set and also the labeling part. So the first one, it's this slide is called chroma separation data augmentation, and it's a kind of like the simplest method. It's inspired by like the green screen technique that is used in movies. So like we have usually actors that are filmed in front of a green screen, and then the background is later like removed and changed for another one. And so this chroma separation allows us to isolate an object from the background. So in our case, how it works. So for the formal object like this cable here, we have that the object is recorded or like photographed in front of a single color background image like this one. And then the green color, the knowledge of this green color is used to like separate in a kind of automatic way the background from the object. So it's possible to obtain this kind of mask here. This is like a semantic segmentation mask in this case. Then this mask is used together with the input image, some like synthetic background is used to generate many different images like these ones, without having like to take an actual real world image of each of these. Okay, so from one simple image, we can generate way more images in this way with some like additional backgrounds. And we can use obviously not just one background, but many different backgrounds. And in this way, we can generate a very large data set to be used for training our perception system for cables and wires. Obviously, this is usually paired and is kind of implicit here with some augmentation techniques. So that augmentation is used to change a bit the image in order to make it different, and so to allow the learning system to, let's say, learn and generalize better. And this is used quite a lot. As you can see, there is a lot of augmentation in terms of blurs and also some deformation of the backgrounds, and also different shape, different colors, different contrast and brightness, and so on. So all these like techniques, data augmentation techniques, are used to make the data more robust and help the learned model generalize better to real-world conditions that are not present during training. So this is like the simplest pipeline, chroma separation with the green screen and some synthetic backgrounds plus data augmentation. In this way, we can generate a data set of our object of interest. This is this case is shown for cable and wires, but can be applied to any kind of object, really. So what are the advantages of this approach? It's the first one is that it allows us to rapidly produce large varied data set with minimal human effort, and it's gonna enable like this model to handle like through the data augmentation different lighting, different backgrounds, different object appearances in an effective way. The limitations that are shown here is that we need initial human input in order to record the object of interest in front of this green screen and tune these parameters. There are a couple of parameters that need to be selected in order to extract like this mask here. And the second one, it's kind of like hidden here, is that obviously you cannot do this if you have a green object in front of a green screen, because you cannot like differentiate the two of them. So we need always to use a background that is quite different from the color of the object. that you want to segment from the image. So this is the first method. Another powerful approach for generating kind of like dataset for deep learning system is synthetic image rendering. In this case, I'm showing some images rendered through Blender. That is like an open source environment for this kind of photorealistic rendering of scenes. So in this approach, cables and wires in general are modeled as like some random curves and random splines in the 3D space on the environment, and in particular, the presence of this synthetic environment allows us also to randomize like many properties of the object in a very effective way with zero human effort, because we can change the color, we can make the appearance like with the stripes or not stripes. We can change the radius, the thickness, and also like the way the material appears in the image. So how rough is the material, or if it is like a cable, or it is like a rope with some like threads and so on. So we can do a lot of things. We can also add a random object together with our scene here. And so in this case, I've just shown some backgrounds, quite complex, but just background. But obviously, you can also add in the scene some rigid object that you know are present in your environment and you want to be like robust against of. And once so we generate this shape, we fix all these parameters, we can render these images here. And at the same time, the advantage of these synthetic environments is that they allow us also to have like ground truth, error-free, very precise labels, segmentation labels. So in this case, these are instance masks. So for the instance segmentation task that I was describing before. And so these labels are perfectly accurate, high quality, and so for training purposes, they're very good, because there is no like ambiguity about some errors that can be present during the labeling process for the dataset. And clearly, okay, this is just one random object, but if we have like a specific environment we are thinking about specific environment with some like metal backplate, some electromechanical component like in switchgear manufacturing, maybe we can add these wires in this specific environment and so construct a synthetic environment that is closely resembles the real one. And this way, maybe our dataset is more as let's say a distribution more closer to the actual one present in the real world. So this is an example of like getting everything from a synthetic environment in Blender. And a third approach that can be used for dataset generation involves this human-assisted real images labeling. This is something that we tried to do 2 years ago, kind of. And the idea is to complement synthetic data generation. So this method addresses the main limitation of fully synthetic dataset that despite being like highly scalable, of high quality and perfect, in these synthetic environments we may fail to capture like real world details and like complexities, such as like a very specific lighting condition, or some like very specific material textures, or some occlusion, some other objects that are difficult to model in the synthetic environments. And so we need another way to like we need to rely on some real world images, like really real world images, but we don't want to spend a lot of time doing the annotation, the labeling. And so the idea is to use this human-assisted procedure. And so in this method, we have these 4 steps. We have a human operator that is providing sparse, in this case here, is providing sparse annotation of cables or wires by like putting some labeling key points along each object. And this, so instead of manually segmenting like a wire pixel by pixel, so the operator is just using this BR, this tracking pen, to record some these key points. So in order to provide, let's say, a minimal but informative guidance for the annotation process. Given this, then there is a robot with a wrist camera that is going to capture multiple images of the scene from different position camera angles. And so the robot is going to move along a given control trajectory, and it's going to record these many images from different viewpoints. And so this creates a rich dataset of real-world images with minimal manual intervention. Then there is an optional, let's say, correction procedure, refinement procedure that is used to transform the sparse this key point annotation into a dense masks in order to obtain this kind of like output. And then this, for all the images that our robot has collected, we can obtain like a fully annotated dataset. So here I have some video showing like the process of both labeling and collection of images by the robot. So on this side, we have the labeling part. As you can see, the human operator is doing this key point annotation along the two wires. And here we have the wrist camera of the robot that is collecting like all the images from different viewpoints with different angles, etc. So in this way, we are saving all these images together. And okay. And finally, there is like the third step. It's one about the correction procedure that I think is clear down here. So the thing is that we can have some annotation error and inaccuracies due to like the camera, the robot, or the human operator like labeling a point that is not exactly on the object of interest. And so like here, so this red dot is where the actual input key point was placed, but instead should be like shifted at the center of the cable. And so we have, in this case, we have developed this correction network that is gonna like take these crops around the key points, and it's gonna compute this approximation of the cable center line. It's gonna shift and correct these points at the center of the wire. And once we do this, we are in this phase here, then it's kind of easy to obtain the final masks in this way, and then that are combined to the final, let's say, output of our dataset for both semantic segmentation and instance segmentation. So a key strength of this approach is that it can be combined with synthetic dataset, and in particular, we use that in that way. So we have a section of the dataset that is using fully synthetic data, so large-scale data obtained with very random backgrounds, very random environments, lighting conditions, and so on. And then we are combining this synthetic dataset with a smaller portion of this weakly supervised human-assisted real images in order to compensate for the subtle, unpredictable variation that can be present in this given real-world environment. And in this way, we create a rich and diverse training dataset that in which we exploit like the advantages of both. So we have the scale and accuracy of the synthetic environment and the realism of the actual real-world images. And finally, I think the last method that I'm going to talk about data generation is the one involving foundation models. So in recent years, we've seen that we are experiencing actually that the field of artificial intelligence has seen the rise of these foundation models. So these are like large pre-trained AI models that are capable of performing a wide range of tasks across different domains. And unlike like traditional models, which needs to be like trained from scratch for each of like specific tasks, specific applications, these so-called foundation models are trained on a massive dataset and are able to generalize to new tasks with minimal additional effort, sometimes even zero additional effort. So in computer vision, there are these like kind of foundation models that can take like the input image and also a set of like points or prompt, let's say in general. It can be like even some points, a bounding box, or even some text. And this can be used to automatically generate like a segmentation mask. Okay. So these models are very effective and they do work quite effectively also for our object of interest like today, but are also quite heavy in terms of computation. And so they are difficult to directly deploy on a robotic system. Okay. So what we try to do in our group is to use them for generating deep learning task-specific data set. So this heavy computation time can be a bottleneck, let's say, when deploying on the real robot, but are not so dramatic, let's say, if we do like offline for generating a data set. And so the idea is that we can directly deploy these kind of systems to label our images and in order to build the dataset. So the method I'm showing right now is very similar to what I just described right now, the slide before. So also in this case, we start with a sparse annotation of a few points on the object of interest. And then, but the difference that we're going to use in this case a pre-trained foundation model in which it's going to like automatically convert these minimal like inputs, these key points into the segmentation masks. And the beauty, let's say, of this approach is that it works without any fine-tuning or prior knowledge of the object. So it's highly versatile for different type of deformable objects. As you can see, like here we tested with different like ropes and with very different textures, and it works for all of them. And in addition, in order to, like before, in order to expand our data set more, we use a camera with a wrist, a robot with a camera on the wrist, and as the robot moves, we're going to capture like these images from multiple angles and multiple positions, and we're going to use this very first single annotation in order to label all of them. And also, in this way, we achieve the same result as before, so we are able to generate this large and diverse set of samples with very, very basic human effort. That's just the one of drawing some key points on the very first image. So this is a three-step process. So first, we have the camera-equipped robotic arm that's going to collect a set of images from different viewpoints by moving along this like ellipsoidal trajectory in this case. So it's going to, in particular, keep the object of interest in the camera field of view. Then second, we have a user that's going to provide this sparse annotation by marking like few key points on the object of interest in the set. So in this case, I'm showing like the example for some clothes, because we tried also with different kind of deformable objects like clothes and like garments, but it works in general for any object. So we're going to provide these points here on just one image, and then we're going to convert this sparse annotation, let's say, into a dense labels like these ones here with these like masks here, using in a zero-shot mode, so without fine-tuning these foundation models. And so this segmentation mask is like ready for any robotic perception and manipulation task, because we can build any dataset in this way. And this is the complete pipeline. And because we assume to know, we use the robot to know the camera pose in the world coordinate system, we can kind of convert just one annotation for all the set of images taken from the robot. And as you can see, like this, like the pipeline, and here we have our foundation model that is so here we have a foundation model that is used this way to get this mask instead of the previous approach about the correction procedure, because the foundation model in parallel is also doing some kind of correction to make the points coherent with the object that is present in the scene. Okay, so these are, I think, 4 ways that I just described to build our dataset for learning for the perception part of our robotic system. So Right now, I'm gonna talk a little bit about the state estimation. So that's because right now we are just describing way to build this set of this pool of images that we can use maybe to do some segmentation of our objects. But in robotics, it's not just about segmenting an image. We need to be able to describe the state of our object in order to decide how to do the manipulation as well.
Alessio,
So
may I interrupt you just a second?
yes,
Maybe do you think it would be possible maybe to take a break on, do you think it's a good
maybe,
moment in the presentation or a
maybe
bit
yes,
later?
because I think we are kind of a bit like mostly halfway. So yes,
Okay, then I would suggest to take, let's say, 10 minutes break and we connect again.
okay,
Okay?
great.
Okay. Okay, I think we can start again.
Okay, great. Okay, so we now have like a dataset that can be used to train our perception models for our cable wire recognition task. And so for our robotic manipulation task, the perception system needs to do like some things. So we need to actually determine the position, the shape, and also the motion of each deformable object in real time. And so this requires not having just a simple, let's say, segmentation of our object, but we need at the end to reach this instance segmentation task. So to be able to assign this unique ID to every yellow instance in our image. In addition, we need also to extract the object state. So we need our perception system to provide a detailed description of each object configuration as a sequence of points in both like 2D state, but possibly let's say even better in the 3D state. So to be able to have the 3D state of our system and also able to track that effectively. So in this set of slides, we will like build upon this concept and we'll explore how to move from like this simple like instance mask to full like 2D and 3D object state estimation tracking. Okay, so let's first focus on just on the 2D perception, and then we're gonna talk a bit also about the 3D part. So the general approach that we have found to be like quite effective in our case, like for our experience, is to first perform a semantic segmentation phase in which we kind of just differentiate between the background and where there are cables and wires. And in this case, we can like directly exploit the data that we just talked about in the previous part of this training. And once we have this, then we can add also a second part in which we process the input image and the obtained mask in order to find the individual states of each object of the scene. So in order to reach both the instance segmentation mask and the 2D state with a sequence of key points describing the state of each wire in the scene. To do that, a general pipeline that can be employed that we deploy several times with kind of good results is this one. And as you can see, it's kind of complex, and I'm gonna try to like process that part by part. So as you can see, the first part is to generate this semantic segmentation mask that I just said before. So given the input image, we obtain this segmentation mask. And then together, this input image and segmentation mask are used in this pipeline that goes in this way in order to obtain the final spline points representing our state, the state of each of the wire in the scene, and this instance mask. So the first step, like given once we have this mask, is to do image simplification. So in particular, we notice that a good way to represent our cables and wire in the scene is to have like a graph-like representation of them that is going to allow us to process them effectively and also to do like manipulation and everything like in a compact way. So to describe the state also in a compact way. But in order to obtain this graph representation, the first step is this image simplification. So how can we generate this graph-like representation? And there are three different ways that we tried in the past. One of them is through a pixel segmentation, like this one. So the idea is to group together pixels of the image that are similar, like in terms of visual properties, like coherent into coherent regions. And this way we reduce the image complexity while keeping important structural, like semantic information of our objects. So this is one way. The second way is this one is a skeletonization, in which instead we kind of like do an iterative process in which we thin the binary mask down until it's only 1 pixel wide. And this approach is very popular also in the research community across all the methods available in the literature, because it preserves the topology of the deformable object quite effectively, and is also computationally efficient, more computationally efficient than the superpixel segmentation. The main problem with skeletonization is that the accuracy of the result depends a lot on how clean, like how good is your segmentation mask. An alternative method is this one that's just strictly called sampling in this case. And this is instead a more like direct approach in which we sample like nodes from a distance transform image. So from the mask, we do like a distance transformation, and we do this point sampling in order to obtain these nodes here. And this sampling approach is like the most efficient and the most robust across all these three methods. So when the mask is kind of noisy or like imperfect with some like wrong like object in the scene, then maybe this is the best approach. So once we do this, we have done this, we kind of need to decide how to merge these nodes, this object into like, in order to obtain, to move like from here, like in this case it's shown just for this segmentation, but we can think that to have like any of the three methods and how to move in this direction. So there are two ways in which we can move, we can merge these like nodes or these sections of that we obtained before. And so that's two methods, tracing or merging. So the tracing process, I think, is kind of like easy to understand from this illustration. So we iteratively, gradually extend like a path that's going to be for us our section of the wire that we have detected by adding step by step new segment and new nodes one by one. And each update, so the way in which we decide which node to add depends on the portion of the path that's already been traced. And so this is like kind of a local and sequential operation. The way in which we select which node to add is usually based on some cost function or like color similarity or like some metric about the curvature or distance, or possibly also some data-driven tracing guided like neural network that's gonna predict the most likely path region. In alternative, we can have like this merging based here, this merging based algorithm that I instead offer a more global approach. So the idea is that in this case we have already some sections of our cable or our wire already detected, and we need to decide just how to merge them. And so also in this case we can rely on some neural network for some similarity metric, or kind of some like there are also some ways in which you can use some bending energy criterion in order to obtain the smoothest path possible that we can think about like the best solution for our cable. And the main advantage of merging over tracing is that with merging we can kind of like process all these operations more like kind of in any order or even in parallel, which makes these merging procedures more efficient than the tracing one. So either the two, at the end, we're able to obtain kind of this, we are kind of in this part in which we obtain the individual wires, individual cables in our scene. And the last part, the last step that we need is the one to about that I call crossing order determination, but there is not a real standard name. So the idea is that when there is the intersection, the crossing between different cables, different wires, or even the same cable that is like overlapping with itself, it's essential kind of to determine which segment lies on the top, because this information is critical for our robot, because maybe we want to pick the cable that is at the top of this crossing in order to avoid like doing some entanglement with other wires underneath. So also in this case, there are different ways to do that, and the two main strategies is either to use like a learn classifier, so a neural network again that is gonna take this crop the image around our region of interest. It's gonna like predict whether like the blue cable is on top or not of the crossing. In alternative, there are some like more standard and like old school ways, like some color-based score function in which we can compute the color variation along like the region of the crossing, because the idea is that the segment that is at the top is going to show less color deviation due to having like fewer occlusion effects, because usually if you have like intersection, a crossing, then you have some shadow and everything, like this yellow cable here. So this is kind of a clue about the fact that the yellow cable that is going this way is like at the bottom of the cube. And so we can compute this color deviation and can use that to understand which one is at the top or not. Okay. So given that we reach like the end of this pipeline and we are ready to obtain like the final mask and the final sequence of spline points. So this is a video demonstrating one of the proposed systems performing this shape estimation in 2D across 3 scenarios, let's say with different backgrounds, and 3 main scenarios with different complexity levels. So at the beginning of the video, you have seen like this one is like a more simple like wood surface. Then we have this more complex chaotic background with a lot of like different chaotic backgrounds. And this one, I think, is the most important one, is the one that in which the cables are placed inside like a electrical panel. It's not really like crowded like a real one, but it's still like in a relevant situation, relevant background. And as you can see, on this side, you have the visual system performing like the segmentation of the cables in real time with a frame rate like more than 30 frames per second in a kind of like effective method. So this is like a good result that we're able to achieve right now. Building on this discussion about 2D shape estimation techniques, I think it's clear like about given what I already described, that the accuracy of the extracted cables and wires from the image so depends quite a lot on the mask or the input mask that we're using. This because most of the pipelines that are used right now are based on this like idea that first I do this semantic segmentation, I use the mask, and then from the mask I can obtain everything else. So it's important to evaluate the robustness of each of the methods under like some like not perfect masks, but more like degraded segmentation conditions. And so this is just a simple plot I placed here to give a feeling about this. So the idea is I do this iterative erosion process with multiple steps to simulate the effect of a poor segmentation mask. And I compared like the 3 simplification methods that I described before, and I'm going to compare like from a qualitative point of view, which one like is able to provide the most robust solution. And it's clear that the sampling-based method, as you can see, remains stable, even if with a mask that is really like poor. Like in this case, it's really poor, but we are able to obtain the 3 like instance in the correct way. And this is not the case for the other methods. And this sampling methods is robust because it's entirely based on this graph-like representation of the scene that doesn't care a lot about the presence of gaps or even strange elements in the mask itself. So this is one result about the object estimation in terms of 2D perception. So I'm gonna move to the 3D part. So just to recap and to keep like the flow of this presentation. So first we discussed about dataset generation, and then we've used this dataset like implicitly to obtain some internally the object estimation that I just talked about. in 2D, but I think it's clear that a robotic system needs 3D knowledge, of the environment, of the scene, of the object in order to plan and act effectively. And so we need right now to think about the 3D part of the state estimation. And the problem with the formal objects like cables and wires is that they're usually very, very thin. They're usually like a couple of millimeters of diameter. This is a problem for vision systems because if we think about like a standard camera for robotic system, like maybe more from an industrial level, more from a research level, but also within industries, like a real sense, like an Azure, these kind of cameras, they struggle a lot if we have an object with a diameter like a slender shape object, like a cable with diameter below 10 or 15 millimeters. So in practice, they are invisible. You can use high-end cameras like a Zivid or a Photoneo right now that are quite popular, that are able to capture like fine details, but they also come with other drawbacks. So they're usually quite expensive, but most importantly, they're kind of bulky and with a lot of constraints in terms of placement and etc. So they are difficult to be integrated on the robot and effector, so they need to be placed in a static fixed scenario, fixed setup. But this limits a lot the practicality. So and usually they also struggles a lot in terms of speed. So the way the frame rate is also quite slow. So to overcome this, so we had these problems internally. So we struggle a lot to get like the 3D state of our cable and wires. So we come up with a new approach that is based on an idea of multi-view triangulation. So the idea is, I think, is quite simple. So we have instead of using like complex 3D sensors that are either unreliable, like a real sense, or like difficult to work with, like high-end cameras, we rely on a simple 2D camera like this one. And this was on purpose made like with a very cheap camera to show that it's not really important the quality of your camera, as long as you can place it on the robot wrist and you can have an image of a normal, let's say, quality. So with this symbol to the camera, we mounted that on the robot wrist, and we can then use like the 2D perception methods that I just described right now. So in order to extract the state in 2D, so to extract this spline-based representation of our cables in the image, and then we can extract the results from 2D to 3D by capturing multiple images of the scene from different viewpoints, exploiting the robotic arm and the camera on the wrist, and then we can like kind of triangulate these different views together. And this way we can obtain the final 3D state of our cable. And on this side of the slide, I've just placed two examples of what we can do. So obviously in these scenes, like everything is rendered in simulation, like in this side, in Blender specifically, and just the cables are rendered based on the extrapolated like 3D knowledge that we obtain from the robot. So we kind of like process this real world condition situation here, and we try to render in Blender the way the cables are placed, and as you can see, makes sense, makes quite a lot of sense about where the cables are. Also in this simpler case with this this side of the cable here. So this is what we can do, and how does it work? This is like a simple scheme showing like the pipeline. So we start, as you can see from this side, with like more than 2 or more images, in this case K images, taken from different viewpoints. And from these images, we first perform like instant selection modeling, so this blue part in the middle, and here we use standard 2D perception tools that I just described before. And so we're going to identify for each image that we collected, like where is our cable and what is like the representation in terms of a spline curve. And once we have extracted the spline from each image viewpoint, we move here to the 3D part. In particular, if you assume to have like these different images, and this is our estimation of the spline for each image that we got, then we do this assignment of corresponding points across the views in order to match the same section of the cable across different views and in order to do like the triangulation. And in this way, at the end, we were able to obtain the 3D state of our cable. Now, it's a benefit of having the camera on the robot wrist is that we can relate the reconstruction error of our system on two different quantities. One is the baseline, so the distance between the images, like the distance between one image and the next, and also the distance between our camera and the object of interest. So we can optimize these two quantities, so the distance from the object and the baseline, in order to minimize, to make this reconstruction error as small as possible. And we can do this like online during the reconstruction phase because we have the camera on the robot, and so we can kind of solve this optimization problem at runtime and find the correct baseline and distance from the object in order to have the smallest reconstruction error possible. So I just want to show like a video of how does it work in practice. So on this side, you can see a video demonstrating the shape reconstruction process. So we have, like in this case, we're using 3 views. And as you can see, the robot is kind of like tracking the cable and moving forward along its shape, section by section, is kind of like reconstructing section by section the cable itself. And on this side, instead, we have like a testing phase, more like a proof of concept, a demo of what we can do. And in particular, we printed these special fingers for our robot. The idea is that the robot should be able to like slide along the reconstructed shape without touching the side of the hollow circle of the fingers with the cable itself. So this kind of like to have an estimate of how good is our reconstruction, or what is the maximum error that we can get. And as you can see, like we are able also to cope with these small variations in the shape of the cable. So this is the first result that I want to show you today about the 3D perception of cables and wires. So as you can see, the results are quite good and are quite accurate, are very accurate indeed, but there are some limitations. So it works right now only on static scenes. It's not really tracking because it's everything like static. And also we need to do this reconstruction section by section, which means that it can take a bit of time to reconstruct the shape of a very long cable, like if we need to do like section by section. So it's we are using this method quite effectively for grasping, because you just need a simple camera on the robot wrist, and you can like move slightly the camera to get multiple 2-3 views, and then you can combine them and do like estimate the grasping pose to do the grasping of the cable. But you cannot use in a dynamic like environment with proper tracking and everything. So that's why like lately we have developed a new approach that instead is allows like robust 3D perception of these kind of objects in a more dynamic condition, and even in case of occlusions. And occlusions are a big factor because usually it's difficult to see always everything. And so right now I'm gonna like talk about this other method as well. So a key component of this approach, as you can see, in this case, we're assuming to use a DORAM system to do some like routing inside some wire collector. So this is like the standard like setup that we place ourselves in. So a key component of this approach is this part here. So this model-based 3D shape prediction. So here we have a model of our cable, and I'm going to talk about more modeling in the manipulation part. But in this work, we're assuming to have this model of the behavior of our cable based on this coastal throat theory. So, and that is a very, very accurate and precise way to simulate the behavior of this kind of object. The problem is that a model like this is kind of slow. And if you want to do like to use like online with a robot, you need to kind of like instead be kind of real time, like be able to process everything in real time. So the first component here is, yes, we have the model, but we're gonna approximate the behavior of the model with a neural network like in this way. So we're gonna given like the current state of our cable and the action that we do with our robots, we kind of like predict what's gonna be the new shape of our cable. And we're gonna use this neural network that is trained offline with the dataset obtained by the coastal road model, but this is very fast, order of milliseconds of evaluation, and so allows to be used in a more dynamic environment. So we have this model in our tracking, like let's say 3D perception tracking pipeline. So based on our model, we're gonna do the full state estimation of our cable starting from cluttered RGB images. So starting directly from RGB images with no prior depth data and no prior segmentation, we just take the standard, let's say, feed RGB image that we take from the camera, and we do the full set estimation. So perceiving, modeling, tracking the below directly in the real world scenes. In particular, so we enter here with the prediction of our model projected across the different views. In this case, as you can see, we have one view here, like from like the side of the robots, and one from the top, and that scattered these two cameras. So here we have one camera, and here we have another camera. So we are taking like the predicted state of our cable from the model. We are projecting that across the different views, and we are going to use this projection of the state in order to guide the segmentation process. So to use this as a guide for our segmentation, so to know where to look in the image for the new cable. And in particular, we're gonna also, since there is gonna be like a gap between what our model is predicts as the way the cable is and what we can observe from the image, we're gonna use the model just as like a guideline, but then we're gonna update the location of the state of the cable across each view from the vision system. And in the present, the model allow us also to handle effectively also occlusions, okay? Because when we cannot instead like compare what we see from the camera with what the model tells us, we can just directly use the model because maybe we are in a occluded case, and so we cannot do the update with the vision system. And once we do all of this, so we obtain the state across each view updated from the vision system, we can do the triangulation similar to the one that I just described before. So we're gonna like kind of compare the views together. We can obtain the 3D state of our cable. And we tested this across different scenarios with more or less cluttered around, more occlusions, and also different cables to show like how it behaves with different like cables with different diameters, or like even a rope that is really like softer compared to a more stiff and more plastic behavior of an electrical cable. And so these are some results. And as you can see, we are able to, the blue points here, the blue curve is like the projected 3D state across the different views. And as you can see, we can like cope with both like occlusions, like in these cases, but also more like some interactions with like a metal bar. Here there is a metal bar, so we can show that we can keep tracking of the cable even if there are some interactions with the object in the scene. Okay. So in the last part of this of today's talk, I want to talk a little bit about the manipulation. So right now, like given what you observed here, we are able kind of like to have the 3D state of our deformable linear object in a dynamic and also occlusion compatible scenario. So we are everything like from the perception system to to be able to do the manipulation. So we have the state, and so we just need to decide how to do the action, what to do with the robot. And controlling, let's say, doing the shaping, the manipulation of this kind of object with a robot is a real challenge. There is a lot of research going on, and we already have been discussing some of these also before this morning in the introduction, also with the other section of this talk. And the so-called shape control is an essential capability for a real-world robotic application, because shape control means be able to do something with the cable, and it's very important, for instance, for wiring assembly, but also for other domains, like even in surgical manipulation. It's a real struggle, a real important topic. And the success of this shape control depends on the robot ability to predict and precisely adjust how the form object is going to bend, twist, or settle into the desired, let's say, configuration once we finish the manipulation part. So controlling the shape of the deformable linear object is far from trivial, and the physical behavior, let's say, of these deformable linear objects depends on many parameters like the stiffness, the damping, and friction. And all these quantities are often uncertain and can vary from one object to another or from task to another. So in this set of slides, I wanted to focus on the classical, let's say, shape control task. So the idea is that we start from an initial configuration like this one, and we wanted to reach like a target like this. And the key question right now is what are the sequence of manipulation action that our robot should perform in order to reach, like from the start to the target, so to reach the target as efficiently and accurately as possible, possibly also with the minimal number of manipulation actions. And so as you can see, this is like the setup of the 2D case in which we are on a table surface with a single robot doing like pick and place operations, and can seems like to be a bit trivial compared to like industry like tasks, but at the end the shape control task that is used in research, let's say, it's a real good benchmark of how good is your robot doing this kind of tasks, because then it's easy to transfer this for like I don't know, routine tasks, etc. in 2D and everything. So it's really like not a simple like benchmark for research, but it's also important for other like more higher tier, let's say, objectives. So one way to do this, and the standard way that has been explored a lot in the past, is to use traditional models. So to model like the behavior of our cable, like what I already talked a bit for the tracking as well, and then using the model to predict what's going to be the best action. So this, like, say, physically grounded approach makes sense, but the problem is that usually these models are quite expensive to evaluate and also are quite sensitive to model inaccuracies. So like it's difficult to model exactly the behavior of this rope against this like cloth surface underneath, because you have a lot of friction and maybe it's not uniform and so on. So I'm going to show like an adaptive approach that we have developed, and it's working quite well. And it's based on two different type of yellow models, both a physics-based analytical model and a neural network model. So the analytical model is that I just said before, can be really like physically accurate, but is usually computationally demanding and requires also careful choice of the parameters of the model itself, but also other parameters like the integration time and simulation steps in order to maintain like a simulation that is also stable. And at the same, like in contrast, the neural network model can efficiently approximate the analytical model while providing at the same time a significant boost in terms of performance, computational performance, and also stability. And I already talked a bit about using a neural network to approximate, let's say, a physical model. It was for tracking, and a similar thing is done here for manipulation. So the proposed system operates in two main phases. We have first a training phase in which the analytical model is used to build the dataset. So to generate this diverse dataset that is used to optimize the neural network model, so down here. And then we have an online phase in which the trained neural network model is the only one used and is leveraged to perform the shape control task. In particular, is leveraged to select the best action, and then that is going to be applied by the robot on the system, and we're going to get the result and the updated state of our system, of our deformable object. The neural network model offers two key advantages. The first one is the differentiability. So it allows gradient-based optimization. And the second one is the fast inference speed. So allows real-time manipulation and adaptation that are instead not possible with the analytical model. And we're going to use as I said, the neural network model for two different things during the online phase. So one is to estimate the action to perform given the current and target configurations. And the second one is to update the model parameters to bring the prediction of our neural network model closer to the real world, let's say, observed behavior of our deformable object. So briefly, this is the training phase. So we start from a simplified mass spring model of our deformable object. So we have like the nodes representing the state at the state location of our object, and with some torsional spring and some like axial spring between the nodes itself. And we have also energy dissipation introduced through a friction term, a viscous friction term proportional to the node velocity in order to produce a damping effect. And this kind of model is implemented like with a mass spring system, and is used to build a randomly perturbed like dataset. So these are all samples of our dataset. So we build many more of these, and in order to then be used for the training of our neural network. And the key behavior of the DLO is governed by some model parameters, in particular some bending coefficient, some damping coefficient, and also there is some mass parameter. And also this parameter, together with like the kind of action that we perform to the system, are used to train our neural network model. As you can see here, so the in is our state input, and here we have as part of this condition on the model parameters. And this is a key point, because in order to have an adaptive manipulation behavior, we cannot use this neural network model, but this neural network model is not a simple one, but is conditioned on these model parameters in order then to be able to tune or align these parameters and to adapt the actual output of V tilde based on what also we change here in terms of model parameters. So this is the training phase. In the online phase, only the neural network model is used, and in particular by adjusting the model's input and output. So what we do, we send as input and output to our model. We can perform two different tasks at the same with the same architecture. So we can do parameter estimation and action estimation. Parameter estimation, that is the one shown right now in the slide, is performed by comparing the observed yellow shape after an action has been executed with instead the predicted shape from the model. And there's going to be like a gap between these two shapes, and we're going to like update the model parameters that I just described before in order to close this gap, and so to have the prediction shape, the shape predicted by the model, to match the one observed in the real system. And we can do it this way, or we can do action estimation. Okay. In which we compare the current configuration of the DLO with the desired target configuration, and we want to determine the action that we want that we need to do in order to minimize the difference, or to bring the current configuration closer to the target one. So in this way, the same generator model, we can do both control, let's say, and adaptation. And this slide shows the overall concept of our online phase, where both action estimation and parameter estimation are performed simultaneously during task execution. And at each step, the neural network predicts, so it's gonna do both, like what's gonna be like the parameters estimation here and the action estimation here. And as you can see, there is like one big loop that is doing both of that together. I want to go on the experiments. So in these slides illustrates the U-shape reaching experiments, in which we use a white rope on two different surfaces. So we have a closed surface with a higher friction and a cardboard surface that is instead more slippery. And in this slide, I'm showing that the same neural network model is deployed on these two, let's say, systems with different parameters. And as you can see, we are able to reach, after 5-6 manipulations, the same level like of accuracy, reaching a target shape. And in particular, it's possible to compare the estimated parameter for the bending and damping. And so during manipulations, you can see we estimate different parameter for bending based on like cardboard or cloth. So in the two different conditions, the bending parameters estimation is the estimated parameter is different, because obviously the behavior of the system is different, and also the same for damping. So this was just for the U shape. We tried different shapes and also different ropes. So like different properties, like black rope is like the thicker one and also the stiffer one. And as you can see, this is clear also the way the system responds to the manipulation performed by the robot. But in any case, we're able to reach the S shape in all cases, and by estimating different parameters. And this is seen also here, in which we show some like results for the different shapes just for the white rope. And we can see that it's important to notice that the same, like similar parameters are estimated regardless of the chosen target shape. So for the same rope and for the same like cloth and cardboard surface of our table, we are able to get like similar parameters irrespective of the target shape. So this means that this parameter really like embedded in the model and not specific to the target shape that we want to reach. Okay, another approach that we can use for manipulation in case we have a dual-arm system is to do instead like a so-called deformation Jacobian, in which we kind of like map the small we want to have a model that predicts how small perturbation in the grippers of the robots are going to affect the pose of our object state. And the next thing that I want to comment this very briefly in this slide is that this is like the same stuff that I was describing before for the tracking. And in that case, we had like a model for the tracking for random inclusions. And the idea in this that is conveyed in this slide is that we can use the same model that we were using just for tracking also for manipulation. In particular, we can perturb the shape of our model like in this way in order to approximate to compute this deformation Jacobian. And online, so we can online compute this deformation Jacobian and apply this control law in order to compute what's gonna be the action of our gripper in terms of like of the two robots in order to reach like these different shapes with different cables. So in a way, the tracking system that I described before can be deployed both like not just for tracking, but also for manipulation in one combined, let's say, framework. And I want to move to a very interesting, the last like example I think that I have in the slide today about wiring harness manipulation. And we already like so far we will talk primarily about cables and wires, but what about, let's say, more complex structure like wiring harnesses? So in the introduction, we have talked a bit about what are wiring harnesses, and we've seen that they are flexible object that extends like standard DLOs by introducing like collecting like an interconnection of LOs at specific points that are usually called branch points. And so this, like, for example, a wiring harness or of automotive, real-world automotive wiring harness. And the goal like should be like, how can I do like manipulation for these kind of objects with a dual arm system like this one? And what I'm going to show in a couple of slides is that we can represent the configuration of our wiring harness as a topological graph that can be obtained exploiting a graph neural network. In particular, the graph neural network are trained in an inductive framework, which means that they're able to generalize to unseen structure as well. And a nice property of this topological graph that we've already seen a bit with cables, that it's robust to noise in the input mask. And we already talked about this, and also it's robust to the presence of connector clips and other fixtures that are very, very common in this kind of objects. And you can see also in this case, all this is a fixture, this is another fixtures, and so on. So real world wiring harnesses are not just wires, but there are also some plastic parts, etc. So we need to have like perception systems that are able to deal with this kind of also imperfections in our masks and so on. And I'm gonna show like with some like at the end of this in a couple of slides also how we can exploit this topological graph to do some manipulation with a dual arm system. In particular, we're gonna show like something about the disentangling. So we want to, for instance, in this case, we have two intersections like these blue dots. We want to know which the action that our robot should perform in order to remove this intersection and spread out the wiring harness properly, because maybe we want to understand better the structure or something similar. So how can we do this, obtain this topological graph that from which we're gonna do the manipulation as well? So a schematic view is shown in this slide, and the approach is based on three main stages. We have a graph initialization. So starting from the input mask, we can sample node edges in order to estimate, in order to have an initial graph like this one, showing, describing the structure of our wiring harness in the scene. And then we have this big learn component that is based on graph neural networks that is used to refine, let's say, clean this initial graph in order to obtain the final topology representation. And there are three main components here. So the first one is the general link predictor. So with this submodule, we're gonna estimate the probability of existence of each of the edges of the initial graph in this way. And then there is also another orientation, inside in which we're gonna characterize the local orientation of the let's say node by looking at the slender shape in the mask. So for each node, we're gonna obtain this kind of orientation characterization. And then there is a node classifier that is used to determine the type of each node, and in particular to distinguish between like normal nodes like this one of class 0 that are kind of inside the section of our wiring harness, and high degree nodes that are instead the ones present at the branch point and also intersection point like here. So all these like outputs are combined together into a solver, and in order to obtain at the end this topology representation. And a nice thing here is that, and this is similar to what I already described before, is that we train this in simulation, so with a synthetic dataset. Also this one obtained in Blender, and the nice thing is that we use this like dataset where the wiring harness are not really realistic at all. So there are no like connectors or like complex structures, but indeed this graph-based representation is robust enough to be able to be trained in this scenario and to be deployed inside the real world like this one, wiring harnesses. So we tested the approach to do some disentangling manipulation tasks. So we want to spread the branches by removing intersections, and we tested that on 3 different real-world wiring harnesses, automotive wiring harnesses. And so this is the idea. We have a 2-arm system, and we want to use 1 arm. So in this case, it's going to be arm 1 to perform the pick and place rotation around the rotation center that for us is going to be like a branch point detected from the topological graph. So with this kind of like trajectory in this way, and arm2 instead is used to keep the other section of the wiring harness fixed in place, because the wiring harness is kind of stiff with like a spring back behavior, so it's difficult to manipulate with just a single robot. So you need to like constrain the system during the manipulation. So this is the situation in this example, just to get a feeling of how it's working. So this is the input topology, and this is what we achieve at the end. So as you can see, we want to remove the intersection, and so this is the robot. This is the robot arm2 doing the keeping the other part of the wiring harness fixed in place, and this is the arm1 performing the pick and place with this kind of motion. And as you can see, we remove the intersection. And we tested this again across different wiring harnesses and different initial conditions, or this like the one shown in this slide. And we have experienced that this kind of approach kind of works. So the idea of approximating, let's say, the topology of approximating the state of our wiring harness with this topological graph is kind of effective, because it simplifies a lot the problem. And yeah, this is like the result. So we reached the end. So I just want to briefly draw some conclusions. So I'm going to start from the perception. So we have seen that synthetic data generation methods are an efficient tool for building dataset for deep learning models. So I've talked about different ways, but at the end, most of the results are kind of based somehow on some synthetic data. So they're very, very effective. And we have seen also that semantic segmentation of the formal linear object is a powerful approach that can be used to simplify the problem of image perception, at least like at the very beginning, and can be combined with a graph-based representation in order to obtain the instant segmentation of the formal linear objects. We have seen also that a graph-based representation of the LOs of the DLO present in the image scene can be extended quite easily, let's say, to also wire harnesses. And so at the end, we can obtain like a common unified approach addressing both like simpler cable and wires, but also wiring harnesses, like the one that I showed right now with the topological graph. And concerning the 3D reconstruction, we're seeing that it's possible to integrate what we have like for 2D, so like instant segmentation techniques and so on, with a multi-view standard stereo reconstruction approach. And possibly we can exploit also a predictive model of the DLO behavior in order to handle dynamic scenes and occlusions. Concerning the manipulation, we have that leveraging a topological representation of the wiring harness within the scene, we have seen that it facilitates the execution of this disentangling manipulation task, and just by using a straightforward but effective manipulation strategy. And we have seen that a neural network can be utilized to create an efficient predictive model of the DLO dynamics, and this is shown both for the tracking but also for the manipulation. And the neural network can be trained by simulating the DLO dynamics through an analytical model, and there are many possibilities. So we have shown something about mass spring, but also with the constant rod. And finally, a key benefit of this differentiable neural network DLO model framework is that it can be conditioned on model parameters, and this is going to offer the opportunity to do gradient-based optimization on the same model for both action estimation and parameter estimation. And so that's the end of my presentation. Thank you for your attention. And if you want to connect, I'll place the LinkedIn QR code here on the slide.
Thanks, Alessio, for the presentation. It was quite interesting. I would like to ask the audience if there are any questions, because now is the question and answer moment. So Alessio will be happy to answer to any doubts. Otherwise, I have actually have a question myself. So I was wondering on from your perspective, from your point of view, how a challenge like the one you faced, so automatization of handling of wire and wirings, could be transferred in a small and medium enterprise context, in your opinion, maybe with a company which has less digital resources and knowledge. So, from your point of view, what would be the challenges and that a company would face to integrate a solution similar to yours?
I think there are many.
Many.
There are
Okay.
many, yes, many from first of all, from the point of view of deployment. This is true like in general, because to run all of this, you need the kind of like workstations and like GPUs and so on, and also, so there's gonna be like, in terms of deployment, a lot of work to be done. And yeah, and then in like, for instance, in this, I'm gonna be back, I go back quite a bit. So if I'm talking about from our experience within the spin-off project, so if you want to do like kind of this, you want to do the testing with the robots, you need the kind of this digital twin, and so you need to have this kind of to be able to obtain this. This means that to have kind of a bit of automatic like automation at the very beginning, even during the design. So you need to have like data and everything. And not all the companies, even small medium enterprises, are using like this at all. So some of them are just using like just entirely paper-based documentation, and it gets like more difficult because you're missing even like from the very beginning some part. If instead the small medium enterprise is more like toward more advanced solutions, like even a bit about using CAD data or using some like having already something ready, then it's easier to connect with other stuff. So this is something, yes, because even if you want to do like the routing of the cables, it's important to know like easily that you need to go from this point to this point. But if you have like CAD data, then maybe it's easy to extract. But if you have just paper documentation, it's difficult. So there are different levels of of challenge, and depends mostly, I think, about the what you get from the point of view of the input of the company. So what you get from the input, yes.
Okay. Okay. So, both in terms of investment for the technological resources for performing calculations, and both also for the basic usage of actually CAD systems. So, starting from the
Yeah,
beginning of having a virtual prototype of the
yes.
products on which you are
I
working, rather than just the documentation.
I think to summarize this, like how the process is currently done, that can be done like really like easy to move forward in a like robotic solution, or really like in a terrible way right now, so it's more difficult.
Okay. Okay, and maybe I would also ask a last question. Um, so I think we already some highlighted what are the main obstacles for integrating solution like these in a small enterprise or medium one. And I wonder if you have um, collaborated already with SMEs. So maybe what you just told me is it come from the direct experiences. So it's quite common that there's such problem is met within SMEs. So it was not just a single case. It was something that happened quite often. Or
So we did some kind of exploration activity here in the north of Italy about especially this switchgear assembly, like how the companies are doing this right now. In the north of Italy is full of SMEs, and it's clear what I already said. So it's clear that not everybody is doing the same way. Some companies are using more like automatic tools to do like that automatically is gonna like tells you where to look in the panel for the for the component and everything. So you kind of have like a system that given the cable is gonna tell you where to look already, and like more advanced, like say companies, even just smaller SMEs, and instead there are other SMEs that instead are entirely like based on old school ways of doing the process. So there are no tools that the workers are using, and so every worker is going like through the documentation and looking inside the cabinet for everything and so on. So at the end is, yes, it's not just one case, it's that the way the small and medium enterprises are working in this field at least is different among them, and so it's also difficult then to propose something in terms of like solution and platform and so on, because the input from one side is kind of different, and so you need kind of like customize a bit based on the each case. And some cases are easy and some cases are not. And that's why also we are kind of like working now quite hard to convert, like my presentation was mostly about like some technologies, but obviously from like TRL 4, 5, then you need to reach like 8, 7, 8, 9, and so we are kind of like pushing in that direction, but it's not easy.
Okay, thank you. Okay, I think everything was clear, and I see no questions from the audience, so I think that we can consider the training to be over. And I hope everybody enjoyed the information, and you're gonna take away from this experience on the challenges and on the possibilities that are in digital manufacturing, in this specific case. Um, um, I would say a quite hard employment of virtual prototyping and more. And therefore, I would like to thanks Alessio for the training, and I would like to greet everyone. And I remind that this training is recorded and is going to be uploaded on the YouTube channel of the SMERF project, as I said at the very beginning. So thanks everyone, and have a nice day.
Thank you. Bye. Thanks, Federico. Bye-bye.
Bye.
Thank you.